So the speaker of our seminar today is Professor Malkhaz Bakuradze. He's from Tbilisi State University. He's an pivotal of Equivariant Bredon Cohomologies, Maskey, Morava K-theory. Please.
Thank you. Thank you. Thank Wanli again for inviting me here, and I'm very glad to be in Prague again, my favorite institute and city. Uh, uh, in my talk, I will mention some old results about classifying Morava K-theories, rings of classified spaces of finite groups, and some new plans how to apply these rings, which are calculated explicitly in terms of characteristic classes and transfers from them to finite dimensional but complex equivariant CW complex. In general, Morava K-theory itself for these complexes are difficult to calculate, but if consider spectra at a spectra, the second term is given by this Bredon cohomology, and I will speak about. So, outline is that after some introduction, I expected the young people some how this Bredon cohomology related to spectral sequence and some complex example for just by action of very classical group like quaternion group, and how the Bredon cochain is constructed by this local system of coefficients applied Morava K-theory for classifying spaces in equivariant sense. And then why it should be convenient, more convenient than usual cohomology, I think. So this is very new. This is just start. But the hope is that Morava K-theory must be give more information than on its particular case, cohomologies with coefficients in field. So Mackey Functor is Functor which J is a finite group here, and Functor assists to which orbit. In our case, classify Morava K-theory of classifying base of the stabilizer of cells with this orbit G factor H. So that this is chain complex. This is usual. It's consider cells in this equivariant sense as orbits, and each orbit has its stabilizer. G is sigma, and consider its classified space and Morava K-theory. This is some vector space because K and star itself is vector space. So we have vectors, and differentials are linear maps. So we have some finite, because for finite groups, K star is finite rank. We have finite matrices. That's if we fix some basis in K star VH. But the hope is that if everything calculated in classified spaces explicitly, including basis and ranks, So everything should be calculable in Bredon cohomology, which is just cohomology of this cochain complex. And especially that this cochain definition also it's not difficult to calculate. It's just given by this formula. And as usual, cohomology ring is just quotient by image of this, by kernel of this trans matrix or linear map by its image. So I just checked for small complexes. It's very easy to calculate, just some work. But idea how it can be applied for equivariant CW complexes for finite G, and X as complex itself is finite dimensional but complex. Many cells. Itself Morava K-theory for X is not easy to calculate, but maybe Bredon cohomology is calculable as first step to, in one sense, first step to Morava K-theory, but another direction is just in applications to topological data analysis, for instance. If we have very complex CW complex, and by some reason there is some group action. So that this is second term of Javakhishvili is given by this second page. So if for some reason these groups will be evenly generated, of course, then in Morava K-theory will be also, this is sufficient to be.
So what is the target? So first of all, I mean, should it be KN somehow, or is that K?
KN Q means
Target.
X is G.
K, but K, then KN.
Where here?
Yeah, K.
K, yeah.
But then also, I mean, so since you have this.
K was equivariant K-theory. Equivariant KN, yeah.
Yeah, but then, okay, but then the other thing, it's sort of like, it's Borel homology, right, or something, because if you have BH, and they are supposed H, so they should be.
Here is written, yeah, for point, equivariant, yeah. So, yeah. Point, yeah. Yes. No. It is.
Yeah, so it's Borel.
Yeah.
Okay.
What is it? Consider maybe. Okay. This is just to give some idea. This is some example, which is non-equivariant contractive because this is conus, some conus of one skeleton of octahedron, edges of octahedron. This is connect, this is some constructed by triangles. So vertices of the octahedron plus origin. These are points, and then edges and two two Tbilisis, two cells. This is two skeleton of a star of octahedron. Okay. And we have natural action of Q, group of quaternions, and just listed which cells we have in this case. And so non-equivariant, this is just has homotopy type of the point, but but equivariant, this is the picture, and here we list the equivariant cells by its stabilizers in order to construct this cochain. So differential is given by this formula, so everything is calculable. And I just omitted the answer, but these are matrices for the differential. If we fix some basis. Now there's some appendix about Morava K-theory for not for you, but for young people. I expect it here. Why we consider Morava K-theory, not K-theory, KO, or ordinary cohomology? Because I think this, in this sense, for this reason, for finite dimensional but very complex CW complexes, the K, how to apply K star BG is much better because this functor is best calculable, if you agree, best calculable functor for BG, for classified species of finite groups. And many groups, as it was conjectured by Hopkins, Carr, and Ravenel, should be good in the sense that Evelyn generated, but you, Igor Klis, disproved this by prove that not all groups are finite groups are good, but more or less many groups, many examples of groups are good in the sense that they are Morava K-theory rings not only evenly generated, but generated by chain classes and transfers from chain classes. So bifactorial and natural classes, and we can track its restrictions if consider subgroups of G or transfers. So this is what is used in calculating in Bredon cohomology. So everything should be
even minus the all. So dimension of the even part minus the dimension of the odd part.
dimension of what?
Dimension of the even part minus the dimension of the odd part.
But if group is good, yeah, we consider good groups here. Yeah. Only odd dimensions. So odd dimensions are 0, is evenly generated. Evenly generated by characteristic classes. So that it's not very hard to fix even basises in terms of chain classes or its transfer. So that Bredon cohomology should be calculable in principle. In contrast to Morava K-theory itself, for this finite dimensional complex. Here is the definition and of good groups I said already. Here is a list of groups which are good, sense, families of groups and with definiteness. And this is just for give you an idea how it looks, the rings. Here G is dihedral group, general quaternion group or semidihedral group. And here is definition of group and the Morava K-theory. Here is chain classes, represent complex representations, and chain classes are defined. There's C, X, and SI. And ring itself are quartet ring by 3 generators. And relations are listed here. Consider cases. So these are additional non-main relations, but are interesting. So these are all generators, and it's pardon. Oh. Okay. Some should be some modified. I also consider some modification of usual differential here. Okay. So I also consider this linear map, not only restriction, but add transfer also. So consider not only restriction, but first transfer to global group and then restriction. This linear map can also differential. So also gives some cohomology, which is not exactly the Bredon cohomology. But in some sense, the result of this cohomology theory with respect to this definition looks something better than Bredon cohomology in some examples. In a sense that contains richer information consists of generators of this Morava K-theory of stabilities. So for some examples, I try to calculate this cohomology, some modified Bredon cohomology, let me say so. It also makes sense. Okay. Of course, here is not the place to consider the methods how to. Okay, if we fix basis in Grobner basis, for example, we have linear map, we have some metrics, but there are some methods how to reduce this, how to find the kernel of images. This is also the task, okay? Because large matrix, it's how to obtain so-called Smith reduced form and so on. This is also possible in small examples, of course, which can be done by hand. Now, even consider very, very simple case. G is Z2. Z2. What is the example of this case? This we know that we have a so-called KR, a real K theory defined by Atiyah. Yeah, we are a real band is not a real but complex band, but with equipped with some involution on base space, such that involution is not free in general, such that over the fixed points, this involution acts as conjugation in fiber. And of course, this projection is respects this involution, and he considers such bands with he called this or maps of bands, real maps, and real sum and real tensor product and so on. So he puts everything in a real category and consider, as usual, Grothendieck group of such construction. He obtains a real K theory for compact. For he considers Atiyah always compact CW complexes. But of course, in non-compact case, just Alexandrov compactification and so on. Now, in our case, we if consider not compact but finite dimensional, maybe not compact, but finite dimensional CW complexes, what we have first? We have so-called stabilization and splitting theorems by Hirsebruch. Sorry, by I mean, every band is XCW complex of dimension n. Every band C of dimension n, if it's a real band, rank of n plus 1, it's a section. If complex band has some function for quaternion as well. Huesmeler. By Huesmeler, we have two non-equivalent versions of splitting and emitting theorem. We can transform these theorems in equivariant case when, for this simple case, the group is simplest group, and obtain so-called finite real K theory. I mean, for fixed dimensional CW complexes, we get K theory, which is generated by bands of finite dimension. And because of stabilization, this is isomorphic to Atiyah's K theory. In case of very low dimensional 1, 2, 3 cases, the dimensional CW complexes with involution, somehow some people apply this in for topological insulators like this. Has some application. So that this is done in works by me and Ralph Meyer. Ralph Meyer. So, from Göttingen University. just very new. It's appear in the archive and some Georgian journals. So another idea to continue this one and do everything for other finite G's. But in this case, of course, conjugation is not linear, yes? So conjugation is not linear, but we want, in case of general finite G, consider G a covariant K-theory. So this linear representation of G, of group G, and to develop again G equivariant finite K-theory. And this will be difficult, obviously. And one idea is to apply again Bredon cohomology on Mackey Functor in Morava K-theory. And Morava K-theory is, of course, for when Kn, when n is 1, is just direct summand of complex K-theory modulo P. Is some, in particular case, there is some close relationship with K-theory, complex K-theory. This is not just idea, no new results there, but just some proposal which we propose. So I can finish now.
Okay, that's, okay. So,
Because now young people don't need to consider many definitions, you know everything.
better, yeah.
Actually, I have questions.
Can you say something about the factor, born with the factor, but you can compute it in some cases. That is the Mackey Functor.
Mackey Functor. It depends. You consider this CW complex action of G, and for what is the so what is the cell in equivariant sense? Not one cell, but its orbit, you know. So Mackey Functor, what is? This is not cohomology with fixed coefficients, but each orbit, for each orbit in the place of coefficients sits Morava K-theory of the stabilizer, classified or stabilizer of corresponding to this orbit. So that this is sum of sub-vector spaces and the differential is some block matrix.
I don't know whether it's
So local system of yeah.
Restriction marks.
If you consider some group and its subgroup, the stabilizers greater, you know. So it's some related. Mackey Functor is not only orbits, but it's calculated with the restriction functors, also transfer functor, and yeah.
The numbers. The numbers from the restriction.
Mackey Functor is some collection, not only orbits and its values, but yeah, but some steps. Yeah.
So when you say application,
I want to have application, and we just have some start of the proposal.
I,
Applications seems to have in low dimensional but complex CW complex, which has physical
it would only evolution.
yeah, low dimensional but many huge
But that's because even the cohomology explosion.
yeah.
But if you work in something better than classical, right?
So first step is just to see what is done for ordinary cohomology and replace ordinary cohomology by Morava K-theory for the first steps and see what happens. And obviously, this is more information than Morava is more information than ordinary cohomology. This already gives you something.
Not complicated.
Yeah. Not complicated, but for classifying spaces, Morava K-theory is better calculated than cohomology. You know, better. Yeah. Yeah. Consider, for instance, cyclic group of cyclic group for P is 3, for instance. Yeah. P is odd. So cohomology is different, yeah? But Morava K-theory is better because it's just Morava K-theory at P that is just one generator. Okay. One generator, say U, and P. Okay. Okay. So that
Intermediate better. Better. What I mean, you remember I took about Morava theory for information because people work before full, yeah? Because they meet with the doctrine,
yeah.
then they apply Morava.
So I have experience in calculating and classifying spaces for good groups. Okay. Professor Chris introduced it for odd piece, for any odd piece. They are bad groups, not good groups. Let me say bad groups. But
I think the current interest is going to find out why the bad groups exist and what they are.
yeah,
For example, there is a conjecture that if the group has movable multiplier that's non-zero, then it's a bad group.
mhm.
Like P group, let's say. So I don't know if you can make a work of that. I mean, whether movable multiplier goes zero implies that it's a bad group. I mean, it's like the cohomology example is known to be a bad group now also, but I guess there is no general argument. But it seems it should be true. There's something to do with like rationality, seems to be that there are counterexamples to that, even as are groups where maybe the nether problem
Mhm.
fails over C or something like that. So those are open conjectures now. So maybe in that direction I'm able to proceed.
Yeah, yeah.
So yeah, it's a more question. Please keep that.